Hello everyone, my name is Silvio. I am PhD student at Fluminense Federal University from Brazil. And the second author is Professor Kazianko, that is professor at Federal University of Santa Maria in south of Brazil. So we will talk about this paper named Machine Learning Methods Assessment for Denial of Service Detection in Wireless Sensor Networks. We will start with an introduction, then I will talk about our background, and then I will discuss some related works. After that, I will show our materials and methods that we used to carry out an experimentation, and finally I will discuss the results of this experimentation, and then I will present our conclusion. So in our introduction, the first thing to talk is what is intrusion detection systems, or IDS. This kind of system is commonly used to detect malicious behavior such as DOS, that is denial of service. And this attack usually is carried out by some attacker that aims at to prevent the legitimate user to access some service. Machine learning methods are commonly used to detect a lot of attacks, including DOS, and usually these IDS implemented by using machine learning methods present prominent results. However, just a few works address machine learning in wireless sensor networks, whereas in traditional network it's more common, and there is a lack of a careful assessment to evaluate which method is best indicated to detect DOS in wireless sensor networks. So it's difficult to understand how useful is machine learning methods to detect DOS in a wireless sensor network. So in this work, our goal is to evaluate 5 different machine learning methods to identify which is the speediness and which is the accuracy of each method. We will evaluate the J48 algorithm, the RAP-tree, naive Bayes, random forest, and random tree algorithms. For each algorithm, we will compute its accuracy and speediness when detecting DOS in wireless sensor networks. In order to do that, we will use a benchmark dataset specific to wireless sensor network scenarios, and in this dataset there are 3 kinds of attacks. So we will address flooding attacks, gray hole, and black hole attacks. So now in our background, I will talk a little bit about each of these attacks. The first one is flooding. Flooding attacks exist both in traditional networks and in wireless sensor networks. In this case, we will address a particular type of flooding that exploits a vulnerability of leech routing protocol in WSN. So in this kind of attack, instead of simply launching a large number of random messages, the attacker will send a specific message named advertising cluster head message, used by sensors to advertise itself as cluster head. So this attack will have 2 main consequences. The first one is that all the sensors in the network will spend more time and more energy than necessary to decide which will be its cluster head. The second consequence of the attack is that the attacker will try to confuse the victim to choose it as a cluster head. Consequently, there are other types of attacks that may be carried out by this attacker after playing a cluster head role. Gray hole attack is also called as selective forwarding attacks, where attacker will choose which kind of message will be sent and which kind of message will be discarded. So if one message is discarded by attacker, this message will never be delivered to its destination. Another variation of this attack is the black hole attacks. Different from selective forwarding or gray hole attack, in black hole, the attacker will discard all the messages. So it will not select or randomly discard some packets. All the packets that's passed by an attacker node will be discarded. Now I will talk about some related works that already have performed some evaluation or something similar that we are planning to do in this work. So there are a group of work that consider only traditional networks. As I told before, the attackers, features, devices, and behavior in traditional networks are very different than behavior, features, attackers, models in wireless sensor networks. So all these works are not directly applicable to evaluate the performance of these methods to detecting attacks in wireless sensor networks. There are a second group of related work that consider other attacks than DOS in WSN. So these works are also not suitable to evaluate or to decide which methods are efficient to detect DOS in WSN. There are also a third group of related works that focus on evaluating machine learning methods or IDS techniques for detecting attacks in wireless sensor networks. However, this group of works does not perform any numerical results, does not perform any experimentation to get numerical results. This group of work focus only on qualitative results. Finally, there are just one work that consider machine learning methods to detect DOS in wireless sensor networks. However, whereas our work addressed the network level DOS attacks, this work addressed the MAC layer DOS attacks. In addition, this work considers only two methods. We are considering 5 different methods. Another drawback of this work is that the authors uses a testbed, but the data used to evaluate the classifiers are not published. So it's not possible to reproduce the experimentation. On the other hand, we are using a benchmark dataset that allows everyone to repeat our experimentation and evaluate other methods and compare directly with our evaluation. So regarding our materials and methods, as I told before, we are using this dataset that considers flooding, black hole, and gray hole attacks. There are more than 3,000 samples regarding flood attacks and more than 10,000 samples for black hole and gray hole attacks. So we separate all these samples in two main groups. The first one consists of 10% of all the dataset that was used to train our classifiers. The remaining 90% was used to assess our classifiers. And in this assessment, we will consider both accuracy and speediness of each classifier for detecting its attacks. Each sample in this dataset consists of 22 features, and some features are relevant for detecting DOS attacks, but other features may confuse the classifier. So, in order to reduce this number of features, we applied the information gain algorithm in order to select only the most representative features to detect flooding, gray hole, and black hole attacks. Regarding our results, we found that J48 was the fastest algorithm to detect flooding, gray hole, and black hole attacks on average. It took only 0.540 microseconds for process each instance. On the other hand, we have the random forest that was about to 22 times slower than J48 algorithm. And talking about accuracy, we found that RAP3 and J48 algorithms achieved the best accuracy for detecting black hole attacks. In particular, RAP3 was 0.1 better than J48. However, as I told before, J48 is too much faster than this algorithm. Then we recommend to choose J48 because this difference of timing may allow us to stop the attacker timely. For gray hole attacks, we found that both J48 and RAP3 achieved the same accuracy of 98.11%. Now, considering flooding attacks, we found that random forest is the best. However, remember that random forest is 22 times slower than J48. So if we consider only the accuracy, this is the best algorithm for detecting flooding attacks. But if we consider both flooding detection accuracy and flooding processing time detection, we can choose for other option because we have 4 different algorithms that achieved more than 99% for detecting flooding attacks. As I told before, in flooding attacks, the attacker will send a large number of messages. Therefore, it's easier to detect this kind of attack because such malicious behavior is easily detected by 4 different classifiers. So to conclude this work, we will remember that we assessed 5 different machine learning methods to detecting flooding, black hole, and gray hole attacks that are all DOS variations, specifically DOS in WSN, different from other works that consider other layers, attackers, or other scenarios. We used a benchmark dataset that is provided by authors from the reference number 9 that I will show to you at the end of this presentation. Therefore, it allows us to reproduce this experimentation and assess other methods and extend this experimentation by using or comparing these methods with other kind of metrics. And regarding our results, the speediness was showed that J48 is the faster algorithm. It took only 0.54 microsecond per sample in average. And when we consider both accuracy and speediness simultaneously, the J48 method is the best for all cases. In particular, as I told before, random tree presented a higher accuracy. It's a slight higher accuracy. However, J48 is 22 times faster, and once we can anticipate this detection, it's very important to stop the malicious behavior timely. For future works, we plan to extend this experimentation by considering another matrices, other kind of machine learning methods, including both supervised and unsupervised techniques. So thank you for your attention. For any question, please feel free to contact me. My email is presented on the left of the screen, and Professor Kazenko emails is presented at the right of the screen. And feel free also to take a look in our reference, where in particular the reference number 9 is the most important reference here because it is the proposal of the dataset that we used. So if someone wants a copy of this dataset, please feel free to send an email for this author because this author is open to share this dataset to other people perform similar experimentation and evaluation. So thank you.